Hi everyone, welcome to the Probability and Analysis webinar. Today we are happy to have Zakhar Kabluchko from the University of Münster, who's going to tell us about Poisson zero cell. And let me just recall that the talk is being recorded, but only the active speaker's video is being captured. Thank you. Zakhar, please.
Yes, thank you very much for the invitation. I will be talking about the Poisson hyperplane process. So to start with, imagine that you look at the sky at midnight, then you see stars, and one may try to model them using a Poisson point process, like here. Now imagine that you look at the sky at midday, then you see airplanes, and the trajectory of any airplane is a straight line. So you see random straight lines in the plane. And one can also conjecture that, so something like this, and one can also conjecture that this can be extended to the whole plane so that you can drop infinitely many, but countably many, random lines into the plane. And there should be some mathematical construction describing this. So this is called Poisson line process. And now I'm going to define it in d dimensions. So I will define the so-called Poisson hyperplane process. This is done as follows. So we consider the d-dimensional space Rd and take some line in this space which passes through the origin. So here's the origin and this is a line. Now take a Poisson process on this line. So here are the points of the Poisson process on the line. And then for every point, consider a hyperplane which is orthogonal to this line and passes through this point. So consider such hyperplanes. Every such hyperplane is d-1 dimensional, of course. Now what we constructed here is a Poisson hyperplane process, but with a fixed direction. So all the hyperplanes have fixed normal vector. And now we make it isotropic as follows. We take each hyperplane and we rotate it around the origin without changing the distance to the origin in a random uniform way. So if we are in the plane, we would do the following. We would take, say, this hyperplane, the distance is, say, R1 here. And then we would just take a uniform direction, and we take distance R1, or okay, it's not R1, it's too big. So here is R1, and then we take a hyperplane. And this is called H1, this hyperplane. And then we do the same thing with any hyperplane independently of each other. So we take the second one, say, so this may be R2, the distance, and then I take some distance R2 from the origin and rotate it, and all the directions are uniform on the unit sphere and independent of each other. Now the more precise construction looks as follows. So here is the definition of the isotropic Poisson hyperplane process. To define it, we need the distances R1, R2, and so on, which form a Poisson point process with intensity 1 on the real line in some order. So the points are listed in some order, and we need the directions. The directions are called phi1, phi2, and so on, and they are uniformly distributed on the unit sphere in the d-dimensional space. And all these objects are independent to each other, and given these objects, we can construct the hyperplanes Hi. Hi is the set of all x in Rd, such that, well, the scalar product of x and phi I is the direction, is equal to Ri. And the distance of this hyperplane to the origin is then Ri, or the absolute value of Ri, and the direction is given by the phi I. Now this is done for every I, equals 1, 2, and so on. And in this way, we get a random collection of hyperplanes, which is called the Poisson hyperplane process. So the Poisson hyperplane process is just the collection Hi, I1 to infinity. Now there are certain properties of this process. First of all, it is translation invariant, which is not quite evident if we have just this construction. The translation invariance means that the joint distribution of this collection of hyperplanes doesn't change under shifts by any vector x. So here x is any vector, and if we shift any hyperplane or all hyperplanes by the same vector, the joint law doesn't change. This is not quite evident, but can be proved as follows. So first of all, suppose we have this construction where all hyperplanes have the same direction. Then it's completely trivial that it is stationary, just because the Poisson process is stationary. So this is stationary in any direction, not only in this one, so in any. And now let us do the following. Let us take any hyperplane and rotate it by a random angle or in a random direction, but such that the possible directions can take just two values, so just two possible phis. Now, the hyperplanes which are rotated in the first direction also form a Poisson process, and it is stationary just by the same argument. The hyperplanes which are rotated according to the second direction also form a Poisson process, which is independent from the first one, and it is also stationary. So both are stationary, and the union is also stationary. So if we have just two directions, then the construction would yield a stationary process. But now we can do the same for finitely many directions. It is still stationary. And then we can approximate the isotropic distribution on the unit sphere by a finite combination of delta measures, right? And just pass to the limit, which proves that the collection is stationary. Now, I shall be interested in the polytopes into which these hyperplanes dissect the space. So they dissect hyperplanes, dissect RD into cells or polytopes or cells. And I would like to choose one cell at random. Of course, the number of cells is countably infinite, so it's not quite trivial how to choose one of them, and there are many ways to do this. The first way is to choose the so-called typical cell. I will not talking about the typical cell in this talk, and that's why I just define it in a non-rigorous way. So suppose we have a very, very large window, and in that window we have many, many cells. The number of cells is extremely large. And then we just take one of these cells at random from a very large window. And then we will let the window go to infinity. What we get in this way is called the typical cell. It's a non-rigorous definition, it can be made rigorous. So let me just recall just one result about it, because I will be talking about the other construction in this talk. I call it TD, D is the dimension, and I will be interested in the expected number of phases of such a cell. So I denote by Fk of P the number of k-dimensional faces of a polytope P of P, and I will be interested in the expected number of k-dimensional phases of a cell. Now for the typical cell, Miles proved in the year, or in the 60s, that the expected number of faces of such a typical cell is the same as the number of faces in dimension k of the cube, of the d-dimensional cube. So in expectation, such a typical cell is something like a cube if we are interested in the number of k-dimensional faces. Now I will be interested in a different construction, the zero cell. And it is defined in a very simple way. It is just the cell which contains zero. So if the origin is here, then this is going to be the zero cell of the Poisson tessellation. Zero cell, let me call it ZD. D is the dimension. And now, what is known about the expected number of faces of ZD? So in this talk, I will try to compute it. And what is known? So from the work of Rennie and Zulanke in 67, it is known that in dimension 2, the expected number of faces is pi square half. And then, of course, also the expected number of vertices is pi square half. And of course, the expected number of edges is also pi square half, because it is a polygon in dimension 2. This work has been extended by Solanke and Windgen in 72, who proved that in any dimension, the expected number of vertices is given by some formula involving the gamma function. So it is d factorial divided by 2 to the power d times pi to the power d divided by gamma of d half plus 1. But I will not use this formula in the following. And the same result has been obtained by Schneider, who also proved that this is among all hyperplane tessellations with any directional distributions, this is the maximal one. Now, what is known about the number of edges or higher dimensional faces? Well, first of all, there is a relation. The zero cell is an intersection of hyperplanes or half spaces, which are in general position, which means that it is a simple polytope. I will explain it a little bit later, but in a simple polytope, there is a relation, there is a dense-Somerville relation, which states that the number of edges can be expressed through the number of vertices. So the number of edges, the expected number of edges is also known. And finally, from some recent work, one can also deduce a formula for the expected number of d minus 2-dimensional faces. And it turns out to be 1/2 d plus 1 over 3. So it's a binomial coefficient times pi square. It can be deduced from some recent works. But all the other values were not known as far as I know. And the aim of this talk is at least to state the corresponding formula. So, are there any questions about the tessellation or related notions? Maybe let me ask a question. Can I construct the hyperplane or the line tessellation in the plane in the following way? I take the Poisson process with unit intensity, and then for each point I draw a line in a random direction. Is it going to be a Poisson hyperplane tessellation? What do you think?
I would say yes.
Yes. So if you look at a circle and you try to count the number of lines which intersect this circle, how many lines that are going to intersect this circle? Well, one can take the expected number of lines, right, which intersect it, and one can compute it, and it turns out that it is infinite. So in fact, if you do it like this, you will get something which is dense. You don't see it on this picture, but there are points outside, and they will contribute something, and the picture you get in this way is going to be dense. So this construction yields something different. It's not the Poisson hyperplane tessellation. The Poisson hyperplane tessellation is discrete, which means that any, say, disk or any ball in d dimensions is intersected by a finite number of lines. The number of lines is almost surely finite, or hyperplanes which intersect a ball is almost surely finite. And in this construction, it is going to be infinite. So it's something different. It's maybe a naive way to try to construct it, but it doesn't work. And now the main result here is the following one. So it's a formula for the number of faces in any dimension. So for every k, for every codimension k, the number of faces, the expected number of faces in dimension d minus k, I'm sorry, it should be d minus k, of zd is given by the following formula. It is pi to the power k divided by k factorial times some interesting number which is denoted by adk, and adk is defined as follows. Adk is the coefficient of x to the power k in the following polynomial. I take 1 plus d minus 1 squared x squared, and then multiply it by 1 plus d minus 3 squared x squared. The next one is 1 plus d minus 5 squared x squared, and so on. And this is a polynomial. I don't mean in an infinite series or product here. It's a polynomial. The last term is going to be either 1 plus x squared or 1 plus 4x squared, depending on whether d is even or odd. Now, this formula is claimed to hold only if k is even. So this is holds if k is even. If k is odd, it's a little bit more complicated. It is the coefficient of x to the power k in the following function, in the following series. I take the hyperbolic tangent of pi divided by 2x and then multiplied by the same polynomial. So it's the same polynomial. This holds if k is odd and and d is even, d is the dimension. And finally, it is the coefficient of x to the power k in the function cotangent pi 2x times the same polynomial if k is odd and d also odd. Now, some remarks on this. The main part is to prove this formula without the cotangent functions for the following reason. The reason is that ZD is a simple polytope because it is an intersection of half spaces in general position, and a simple polytope is a polytope in which any vertex is adjacent to exactly d edges. So we are in dimension d, it's a d-dimensional polytope such that each vertex is adjacent to exactly d edges. Or if you are more familiar with the concept of simplicial polytope, this means that the dual, or it is equivalent to the fact that the dual of ZD is simplicial, which means that all faces of the dual are simplices. And I will describe the dual in the following. We will see why the faces are simplices. So here is a simple polytope, and a simplicial polytope is a polytope whose faces are simplices. Now, in the simplicial polytope, there are so-called Dean-Somerville relations. Which allow to express the odd dimensional components of the F vector, and the number of faces, or these numbers of faces, form a vector which is called the F vector. So the odd dimensional components of this vector can be expressed through the even dimensional ones and vice versa. The coefficients in these expressions are Bernoulli numbers, and the same Bernoulli numbers appear here in the expansions of these functions, which is why they appear here. So it's not very surprising that one gets this. The main result is the first formula. Now, what can we say about these numbers? Well, first of all, the number ADK is an integer, trivially, in this situation. So in this setting, it is an integer, and here it is ugly. It may be a polynomial in pi with rational coefficients, or it may be even a polynomial in pi involving the term 1 minus 1 over pi. So this is some polynomial in pi, and maybe with the term 1 over pi. So these values are ugly, and these ones are nice. And I will be talking about the nice ones in the following. Now, I will not be able to prove this completely, but at least I will try to describe some models which are related, and they are also used in the proof. So there are various other models in stochastic geometry which are related to the zero cell of the Poisson hyperplane tessellation. And maybe the most interesting one is a model of random cones. So I will call it just random cones in a half space. These are defined as follows. Take vectors, random vectors, u1, u2, and so on, that are uniformly distributed on the upper half sphere in the d plus 1 dimensional space. So the sphere is then d-dimensional, and the sphere S d plus is defined as follows. It is the set of all vectors x0, xd. So it lives in the d plus 1 dimensional space, such that the sum of the squared coordinates is 1. So it's just a sphere. And the first coordinate x0 is greater than 0. This is called a half sphere. And I take on this half sphere just uniform random points. Let's say if d is equal to 2, no, if d is equal to 1, then this looks as follows. Here are the vectors ui. Here is the 0th coordinate, and here are all the others, and they form a d-dimensional space. And then I will form a cone which is spanned by these vectors. So in this case, it is just this angle. And in general, we consider the convex cone Cn, which is defined as the positive hull of U1 and so on, Un. And the positive hull is just the set of all combinations of the form lambda I ui, I from 1 to n, with all coefficients being non-negative. It is a convex cone, convex polyhedral cone, which I want to consider. So I think it's easy to imagine. And now there are some interesting results about this cone. So in a paper by Barani, Hook, Heitzner, and Schneider, the following fact, which looks quite unexpected at the first sight, has been shown. If we count the number of one-dimensional faces of this cone, one-dimensional faces are just directions, right? The polyhedral directions of this cone, and let n go to infinity, then this converges. So this exists and is finite, which is quite surprising, because if we take, say, a very similar construction, I will take, so you may imagine we take a two-dimensional half sphere, right? Take random directions, span a cone, and the number of the directions of this cone, which are extremal directions, the expected number doesn't diverge then to infinity. You may do the same thing in the balls. I take just points in the disk. Take points in the disk. Take the convex hull of these points, and then it is known, I think, from the work of Renyi and Solanke, that the number of vertices, of course, it goes to infinity, and it behaves, I think, like n to the power 1/3. And here it is finite. It doesn't diverge. And of course, one wants to explain this, and in a joint work with Alexander Marinic, Daniel Timisvari, and Christoph Thiele, we proved that the same holds for the number of faces of this cone in any dimension. So we proved that the limit of fk of Cn, fk is the number of k-dimensional faces of the cone, exists as n to infinity. And the proof is actually very simple. So if the limit of the f vector exists, then maybe the reason for this is that the limit of the cone exists. But if you imagine this cone, of course, it gets close to the half space, right? If you take more and more directions, then the cone converges in some sense to a half space. So the limit is trivial, but maybe we can renormalize it such that the limit becomes non-trivial. And this is done in the following way. We will not renormalize the cone itself, but instead we look at its profile. So recall that we have d coordinates here and one coordinate there. Here we have our half sphere, and let us consider at this point the tangent space to the half sphere. It is also d-dimensional. And then let us project everything to this half space. So the directions which we have, if it's ui's, project to some points, which I call vi. Now, if ui is uniformly distributed, ui is uniformly distributed on the sphere. What is the distribution of Vi? So it has a density on Rd, which looks as follows. Maybe you know what is the density of Vi if d is equal to 2. So if we are in the plane, like on this picture, what is the density of Vi? I think it's a well-known fact from probability theory that if you have a random direction and intersect it with a line in this way, then you get here some distribution on this line, which is a well-known distribution. I don't know. Do you know it? Can you hear me? Cauchy, right. Oh, I don't see the chat. So exactly, it's the Cauchy distribution, and in d dimensions. So here you get Cauchy, and in d dimensions you get a d-dimensional version of Cauchy. Namely, the density is some constant divided by 1 plus the squared norm of x times d plus 1/2. So if d is equal to 2, you don't get Cauchy. It's strange. Maybe it's d/2. I'm sorry. Probably it should be d/2. Oh no, I'm sorry. D is equal 1 on this picture, right? So d is equal to 1 on this picture. So d plus 1/2 is okay. We have d equals to 1 here. Okay, and now what is instead of the cone Cn, I consider its profile. Profile, it's just the intersection of the cone Cn with the tangent space. And it is the convex hull, I denote it in this way, of the points V1, Vn. So I have to take points with this Cauchy distribution and then I take their convex hull. This convex hull is called the beta prime polytope. I will introduce beta polytopes somewhat later, but this is called beta prime polytope. And the question is, what is the behavior of this polytope as n goes to infinity? And now the behavior is very simple because this distribution is a heavy-tailed distribution. It has power law tails. And such distributions, there are limit theorems of extreme value theorem, namely, one can prove, it's a well-known result of the extreme value theorem, that if I take so it's extreme value theorem, if I take all these points, Vi, which have Cauchy distribution, divide them by n, and take the point process of these points, then this point process converges to a Poisson point process with intensity, which is given by some constant, divided by d plus 1, by x to the power d plus 1. So remember that in the formula for the density of the Vi, we had 1 divided by 1 plus x squared to the power d plus 1/2. If x goes to infinity, this behaves in this way, so the tails behave in this way, and the extreme value theory says that there is a convergence of Poisson of point processes. It's a weak convergence of point processes as n goes to infinity. So if we take this beta polytope, right, and if we divide it by n, so this was, I'm sorry, we are in Rd here, and we take this beta prime polytope, we divide it by n, then it converges, at least the points which generated these ones. The point process of the points converges to a Poisson process with this intensity. The intensity has a singularity at 0, which means that the points cluster at 0. So there are many points and they converge to 0 here. There are many of them, but the number of points outside any ball is finite. And so they have a well-defined convex hull. And the polytope, so this beta prime polytope, divided by n, converges to the convex hull of this Poisson process. So our beta prime polytope, let me denote it by PND prime or tilde divided by n, converges in some sense, I don't want to define it, to the convex hull of this Poisson process PD. So I call this process pi d, capital pi d. And now it's clear, or it's rather natural to expect that the expected number of faces of this polytope in any dimensions converges to the expected number of faces of this Poisson process, of the convex hull of this Poisson process, I'm sorry. And now for this convex hull, we have the following result. So it's another theorem, and it has almost the same form as the very first theorem. The expected number of k-1 dimensional faces of this convex hull, of the convex hull of the Poisson process, is given by pi to the power k divided by k factorial times the same number a dk. So it is given by the same formula, but we have here k-1 dimensional faces instead of d minus k dimensional faces. Now, why is this so? This is because both polytopes are dual. Maybe I will explain it a little bit later. Or no, I will explain it right now. So I claim that, and this is the explanation of this theorem, I claim that ZD is dual to, is the convex dual of this convex hull, pi d, up to constants. Why is this? Let me explain this. It's very easy, actually. Recall the construction of the zero cell. It is constructed as an intersection of half planes. The directions of these half planes are random and uniformly distributed over the sphere. The distances to the half planes are points of the Poisson process, R1, then R2, then R3, or maybe the absolute values of these points. So points of a one-dimensional point, of a one-sided Poisson process. So R1, R2, and so on form a Poisson point process on the real line, or on the half line, let's say, with intensity 2, because I take the absolute value. Let me take the absolute values here. Now, the zero cell is just the intersection of all these half spaces. This is the zero cell. And now let us look what happens if we consider the convex dual of this polytope. So first of all, what is the convex dual of a general polytope? A polytope is given or is defined as a set of solutions to a finite set of inequalities. The inequalities usually have the form x. So a polytope is the set of all x, such that x scalar product with some u1 is smaller than 1. X u2 is smaller than 1, and so on. This is a form in which a general polytope, let's say containing the origin, can be defined. So a polytope is a set of solutions to a set of inequalities. It's a set of points which satisfy inequalities. The dual polytope is the set of inequalities which are satisfied by these points. More precisely, the dual polytope is the set of all u such that xu is smaller than 1 for every x in the polytope. So this is our polytope P.
Ich kann dich viel besser verstehen, wenn ich mich mit deiner Sprechweise vertraue.
So if the polytope P is given by such inequalities, then the dual polytope P prime is the set of inequalities which are satisfied by the polytope P. For example, I can take u equals u1, and clearly this inequality is satisfied by all points of the polytope. Or I can take u equals u2, and so on. So clearly these points belong to the dual. And moreover, any inequality which is satisfied by all points of P can be written as a convex combination of these ones. So the dual polytope is just the convex combination of these u's. And now in our setting, we can do the following. So here we have a little bit different inequalities. We have inequalities of the form x times some direction divided by r1 is smaller than 1. So this is our u1. So if we have here a hyperplane at distance r1, then in the dual construction, we are going to have a point at distance 1 over r1 in the same direction. It's just the polar of the hyperplane. There is this well-known construction in geometry. Now, if I take R2, which is bigger, then 1 over R2 is smaller, right? So maybe let me make 1 over R1 larger. So this is 1 over R1, the distance. This is the origin. Then I can take R2. Okay, R2 has this direction, and this is 1 over R2. Then I take R3. 1 over R3, and so on. And now, since R1, R2, and so on increase, in the dual construction, these distances decrease. And now we know that R1, R2, and so on form a Poisson process, which is homogeneous on the real line. Now it's easy to compute that 1 over R1, 1 over R2, and so on is another Poisson point process, but now it is not homogeneous. It has some intensity on the positive half line, and the intensity is given by 2 over s squared, s greater than 0. So these are points with this intensity. And now it follows easily that these points in the d-dimensional space are going to have this required intensity. Why? Well, just if you take these points and take just their radial parts, then when taking radial part, you have to multiply in the polar coordinates by x to the power d minus 1. And this is how you get this s squared, I think. Now, what I wanted to show that the convex hull of the Poisson process is dual to the Poisson zero cell. And now the dual polytopes are related by the following formula. The hyperplane or the hyperfaces of a polytope correspond or are in one-to-one correspondence with the vertices of the dual polytope. And this can be stated for k-dimensional faces of any dimension. So if I have a pair of dual polytopes, then the k minus 1 dimensional faces of P are in one-to-one correspondence to the d minus k dimensional faces of the dual polytope. And this is why this second theorem is just a consequence of the first one. It's equivalent. And in fact, we will prove this one. It's more convenient. Now, to prove this theorem, we have to define the so-called beta distribution. So we have to generalize the concept of the Cauchy distribution which appeared here. Let me do this. So we have to define beta distributions first. Let me consider points x1, x2, and so on, which are independent identically distributed in Rd with the following density. The density is some constant times 1 minus the norm of x squared to the power beta. And this is restricted to the unit ball. This parameter beta satisfies for integrability the inequality beta greater than -1. And this density is called the beta density in d dimensions. Of course, if the dimension is 1, we recover the usual beta density on the interval -1, 1 with symmetric parameters. And now there are some interesting special cases. For example, if beta equals 0, you get the uniform distribution on the ball. Then you just get a constant density, and it is the uniform distribution on the ball. If beta goes to infinity, then this density converges to the normal after the normalization. In fact, all the results, which I will state apply to the normal if we take beta to infinity there. And finally, if beta goes to -1, then what do you think? What happens to this distribution is if beta goes to -1? So what happens to this distribution if beta goes to -1? This function, if we just plug in -1 here, this function is not integrable on the ball. So the constant goes to infinity, goes to 0 here, because the integral of this function is going to be infinite, which means that if beta goes to -1, the constant goes to 0, which means this density goes to 0 pointwise at every point x. But it's a density, right? So it goes pointwise to 0, which means that it should concentrate here if beta goes to -1 in a shell somewhere here. And if beta goes to -1, then one can check that this distribution converges to the uniform distribution on the sphere. So these three cases are special cases. Now, this defines the beta distributions. And there is another family, the beta prime distributions. Beta prime distribution. So to define them, I need vectors which I call x1 tilde, x2 tilde, and so on. IID in the d-dimensional space with density. So the density of the beta prime distribution is defined as constant times 1 plus x squared to the power minus beta. And again, beta is a parameter which satisfies the inequality greater than d half to ensure integrability. Now, our case of the Cauchy distribution is beta equals to d plus 1/2. So it's a very special case. And now we define the corresponding polytopes, the random polytopes, beta and beta prime polytopes are defined as convex hulls of points from these distributions. So the beta polytope PND beta is just the convex hull of x1, xn, and similarly, the beta prime polytope PND beta tilde is the convex hull of this beta prime distributed points. And now the question is, which is natural on itself, is to determine the expected number of faces of these polytopes, and similarly for beta prime. So suppose, for example, suppose I take n points inside a ball of dimension d uniformly. The convex hull is then a beta polytope. And I want to determine the expected number of phases in any dimension. Now, I cannot explain everything now. In order to explain everything, I would need more lectures. But in a joint work with Christoph Thiele and Dmitry Zakhar, we proved a formula which expresses, so we expressed there the expected number of phases of P and D through certain quantities, which were denoted there by I and k of beta and j and k of beta. And now I will try to explain what are the definitions of these quantities. So, and similarly for beta prime polytopes. And by the way, why are we interested in this question? First of all, because it is natural in itself. And second, because if we take beta prime polytopes with this parameter, then we get the profiles of the cones Cn, which I defined. And in the limit, we get this Poisson point process. So the limit of this one is the number of k-dimensional phases of the convex hull of the Poisson point process, and it is dual to the zero cell. So we need to determine the limit of this one, of this polytope, of this number as n goes to infinity to determine the number of phases in the zero cell. And now in this work, we expressed this number through quantities of two types. First of all, let me define the j and k of beta. The jnk of beta is the expected sum of internal angles at k-dimensional faces in the simplex, in the beta simplex. And the beta simplex is just constructed by taking n points in the n-1 dimensional space according to a beta distribution. So it is, let me write it down, it is n over k in the simplex, I'm sorry, in the simplex with n vertices. In the beta simplex with n vertices, which means the following. There are n vertices and any k of them form a k-dimensional phase, so the number of phases is the binomial coefficient, and then we take the expected angle of the simplex x1, xn at a phase x1, xk. So we take the simplex with n vertices and take its angle at a k-vertex phase, where xi are beta distributed in the space Rn-1, so that their convex hull is indeed a full dimensional simplex. So maybe the simplest case, J for 1 of -1. What is that? 4 means that I take 4 points in the 3-dimensional space. 4 points in the 3-dimensional space, and -1 means that these points are uniformly distributed on the sphere. So I take 4 points uniformly distributed on the 2-dimensional sphere. They span a tetrahedron. And this 1 means that I take the angles of this, the solid angles of this tetrahedron at vertices. Now it is known that the sum of the angles of a triangle is constant, but the sum of the angles of a tetrahedron is not constant. It can take an interval of values. And the question is, what is the expected sum of angles of the tetrahedron constructed in this way? And now it's difficult to compute. So it's the main difficulty in solving improving all these theorems is to compute such quantities. And I proved, and that was the first special case which could be computed, first non-trivial one, that this angle sum is equal to 1/8 of the full solid angle, so of the full space angle. So it's 1/8. Similarly, J for 1 of 0, which means that the points are distributed again in the 3-dimensional space, 4 points, sorry. But now they are uniformly distributed on the ball. And for this, the result looks as follows. It is some nice number, pi squared minus 1/8. And of course, the question is how to compute it. So, and that's the main difficulty. And in the remaining, I think, 10 minutes, I can try to explain how to do that. So actually what we need for our talk is the beta prime polytope. So I need a similar quantity for the points which have Cauchy distribution with k and with some very special parameter beta, plus 1/2. This is what we need for this talk. A very special case, but by now there is a general formula for all these quantities, and let me explain how to derive it. Well, just the basic idea, because it's not possible to explain all the details. So the idea of the derivation are the following relations. The Macmillan relations, or they are called Macmillan nonlinear angle some relations. These are relations between the angles in any polytope. So let us consider a polytope P in the d-dimensional space. This polytope has faces. Let me take any face F of this polytope of any dimension. And then let me define, let us consider the following thing. We take the internal angle. So this is the internal angle over the face H at each subface F. So I take, say, it's now difficult to imagine. I take the sum over all faces H here, such that F is a subface of H and H is a subface of P. So of all faces H which are larger than F, which contain F. And then this is the internal angle in the polytope H at the face F. And then we take the external angle, we take the external angle of H in P. And the first Macmillan relation says that this is 1 for every face H. The second relation states that a similar sum with alternating signs is 0. So it says that if I take the very same sum, but we add here some signs, let's say dimension of H plus dimension of P, and then the very same sum, FH times gamma HP. Maybe I didn't say that gamma is the external angle of H inside P. If you need a definition, I can give it at the end of the talk. And this is 0 for every polytope P. Now this is very, I'm sorry, it is not 0, it is the delta function. It is the Kronecker delta function of Fp, which means that it is in most cases 0. It's 1 if F is equal to P and 0 otherwise. And now what I want to do, I want to apply these relations to a random simplex. So I want to take n points in the randomly according to the beta distribution in the n-1 dimensional space. They form a simplex, they span a simplex. And I want to apply these relations to the simplex. Now, it is known that the external angles of such a simplex are easy to compute. The main question is how to compute the internal angles. And they will be just computed from these relations, if it is possible to do so. Now, there are some difficulties in doing this. First of all, the relations are non-linear, which means that I cannot just take expectation, or I can take expectation here outside, but I cannot bring it inside. And I can't write here expectation of beta, expectation of gamma. Still, it is possible to prove that the quantities I and k of beta and j and k of beta. Recall that j and k of beta is the expected sum of internal angles, and I and k is the expected sum of external angles of the same simplex. So these quantities satisfy similar relations. And the properties of the beta distributions are used to prove them. So this is the point where one needs properties of the beta distributions, which are quite remarkable. And this means that if we can compute external angles, then we have some relations between them and the internal angles, and maybe we can compute internal angles by solving these relations. The problem is, of course, that it's very difficult to solve them because there is no guess what the solution should be. But at the very end, there is an explicit formula. So the formulas which I stated at the very beginning were obtained in the following way. First of all, it is possible to compute the external angles. Then we have relations between them and the internal angles. We compute the internal angles just by hand, by software, by computer algebra, and we guess the formula. And after that, we prove that the formula satisfies the relation which are here. So this was the way the formula has been proved. And now we have maybe 3 minutes. Shall I stop here? Probably I can state one more result, or I can stop as you like. So if you have questions, I can answer questions. Otherwise, or I can state one more result. So, is there anything here in the where is the chat? Ah, it's here. Okay.
Thank you, Zakhar. So yeah,
I will stop here. Yes.
How about some questions? Does anybody have any questions?
If you take a Gaussian vector,
yes,
and you sample points with respect to the standard Gaussian measure,
right,
and look at the convex hull, and then start computing expected value of k-dimensional
right.
faces. Is there some formula known for the Gaussian case?
Yes, yes, and it is a special case of this one as beta goes to infinity. But the Gaussian formula has been known for a long time, and it expresses the expected number of k faces. So it can be expressed through quantities of two types. The first quantities are the internal angles of the regular simplex, and the second type quantities are the external angles of the regular simplex. So the expected number of faces of the Gaussian polytope is some functional, some sum over such external and internal angles of the regular simplex. And for these angles, there are explicit formulas as double integrals. So there is an explicit formula for the Gaussian polytope.
And if we have some covariance matrix sigma for this Gaussian measure, where sigma will appear in this external and internal angles?
So in the number of faces, it will not appear in the number of faces because it's just a linear transformation. But if the Gaussian, if you are interested in angles, then nothing is known. Let me think. I think it will not appear at all. It doesn't depend on the matrix. For the these quantities, so the expected sum of the external angles, say, of the simplex, doesn't depend on the covariance matrix for the following simple reason. Well, maybe I cannot explain it so quickly, but the claim is it doesn't depend at all.
Okay.
It's the same. So you may take I mean the following. You may take a simplex according to a Gaussian measure with some covariance matrix. The claim is that the expected angle sum of the simplex doesn't depend on the covariance matrix. We proved it somewhere in some paper.
Okay, thank you.
Any other questions or objections? I was interested, so you know the F vector of these zero cells. Do you know any other characteristics? Can you say anything about the volume, for instance?
Yes. Oh, the volume.
Yes. I don't know how far the
we can,
facets are from the origin.
Yeah, so we can say something about the volume.
Mm-hmm.
There is a formula for the expected volume and for the expected intrinsic volumes of this.
Okay.
So it's explicit. Is explicit formula. Again, involving ADK.
The same numbers, okay.
The same numbers, yes.
Okay.
But the volume is especially simple. So if you take k equals d, then it becomes somehow trivial. You don't need the numbers ADK. It simplifies.
But is it also done through this duality, or there are different arguments to?
So there is a paper by Schneider in which these expected intrinsic volumes are related to the expected number of faces. And what is the idea of the proof? I don't remember.
Okay, I was just
But
curious.
it's not quite trivial that they are related somehow to the expected number of, to the expected F vector by a paper of Schneider.
Okay, any other questions?
I have one more question. I think you mentioned in your talk that if you sample these hyperplanes in a different way, not using Poisson with intensity 1,
Right.
then this expected value of these k-dimensionals is maximized for the Poisson ones.
It is maximized for the isotropic one.
For the isotropic. In which class? Can you?
In the class of Poisson hyperplane processes with an arbitrary direction distribution. So at the beginning, I defined the Poisson process with a single direction. And now one can rotate these planes according to some direction distribution, which may be any measure, any probability measure on the d-1 on the sphere, right? So if you have any measure on the sphere, symmetric maybe, then one can define the corresponding Poisson process of hyperplanes. Say if mu is concentrated on 2 points, it looks like this, 2 directions.
Okay. So if mu is the uniform, then it maximizes, right?
Right, right. Or minimizes.
Okay.
I don't remember, but it is extreme.